Okay, so this is about the buck boost chopper circuit. One of the out of three DCDC chopper that we're going to discuss in EPO 510. So it's a buck boost chopper. So the operation of buck boost chopper mainly to step up and step down, and the assumption before we look into the operations or the operating principle of the circuits, we need to do some assumptions, where the first one will be continuous current mode operation. We're going to consider only continuous inductor current mode. uh, Number two is it is a steady state analysis, and number three is the capacitor is very large. The output capacity is very large, such that the output voltage ripple is zero, or it is a ripple free, and it can be lower or greater than the input voltage, right? So before we again proceed to the circuit operation, a few points that we need to look into this buck boost chopper is that we can see that the output voltage now is negative, or in the opposite polarity that we considered before. Okay? It will be the positive and negative across this resistor. Instead of the previous buck or boost converter, we have plus and minus converter here, but for the buck boost chopper, it is the opposite polarity. So we're going to consider that the voltage output will be positive and negative polarity here. And then this is the important note, whereby if you look at the instantaneous equation, it will be the inductor current equals to the input current that flows out of this node. We have also IC, the capacitor current, and the output current I0. Right, and the arrangement of the circuit components. Now we have the switch, the high switch here connect to the input voltage, and the inductor is connected there, and then we have again the diode is now is reverse arrangement as what we had before. Okay, it is the opposite direction of before, whereby the cathode will be connected to the input side, and the output, the anode will be connected to the output side. Right? Okay. So now, to understand the circuit, now we need to consider two states of the switch, which is the switch, the on state, the transistor is on, and this is when the transistor is off. This is the signals to the transistor, whereby you have a pulse of 1, and then we have 0 when you switch off, then we have 1 again, right? And this is the duration for the turn on. T on is equals to dt, and then we have T off, the duration for the off times, and finally this is the period depending on the switch frequency. This will be the period for the cycles. Okay, right, so let's look at when the switch is on. Right, when the transistor is on, we know that it will appear as a short circuit, and the diodes will be reverse biased by the output voltage here. Okay, it will reverse biased by the output voltage there, so it will turn off. It will be an open circuit. Thereby, you can see that the V in is impressed across the inductor, and the output side we're going to see the IC, the capacitor current, equals to the negative of I0 here. Okay, right. Whilst in the transistor is off, when the transistor is off, the circuit or the switch will be appear as a off or open circuit, and now the current in the inductor will flow through the diodes to turn on the diodes, and that will be the output, the circuit equivalent circuits during the turn off, whereby now we have only VL and V out in the equations. Okay, so let's look at what happens during turn on. So during turn on, we can see that there will be a minus V in plus V out equals to 0. The Kirchhoff voltage law, the KVL across this loop, we're going to say minus V in plus VL, and therefore there will be a positive of V in impressed across inductor causes the current to linearly rise from IL min to IL max. Okay, and that's why you see that it increased linearly from IL min to IL max, and this is because of the voltage V in, the positive voltage which is impressed across the inductor, causes the current to linearly rise from IL min to IL max. And therefore you can see that this is the equation related to it when the switch is on. VL, which is, we know that L di dt is the voltage across VL, equals to V in, and cross multiply, and then we integrate. You're going to see that on the left hand side you have IL min to IL max of DIL equals to V in divided by L, and we have the integration of 0 to T on of the dt. Solving that, you're going to see that IL max minus IL min equals to V in multiplied by T on divided by L, and we also know that IL max IL min is also the ripple of the inductor current, and it is defined by V in T on over L. Okay, and we have to also look at during the turn on, something that we need to note that the input during the switch is on. You can see that IC equals to negative I naught, isn't it? And so it's a constant current which is determined by the value of V out divided by R. It is a constant current. You know, IC equals to the minus I naught. Therefore, if you look at the capacitor current, the pink waveform here, IC is a constant current equals to V out over R, and this will be used when you want to calculate for the ripple voltage. The capacitor, the last section in this buck boost converter is the how to determine the equation for the ripple voltage, and that will help us in finding that. Okay, so now let's look at when the transistor is off. So when the transistor is off, we know that it's a short the diode is off on. The switch is off, and therefore we have only that loop, okay, whereby we have minus VL minus V out equals to 0, and therefore VL equals to minus V out. There is a negative. VL equals to minus V out, whereby we have a negative voltage, output voltage impressed across inductor, therefore causes the current to linearly decrease from IL max to IL min. Okay, so look at the equations. This is the equation when the transistor is off. You can see that VL equals to L di dt equals to minus V out, and we integrate that, and therefore finally we find out that IL max minus IL min equals to V out T minus T on divided by L. And we know that these two equations is equal to each other. You can equate both equations 16 and 17, and therefore when after doing that, you can see that the output voltage now is defined by V in T divided by 1 minus T. So if you look carefully, if D is from 0, D of course the value of D is from 0 to 1. However, if you have D from 0 to 0.5, the output voltage will be lower than the V in, and if you have D in between 0.5 to 1, you will see that the output voltage will be higher than the V in. So the buck boost circuit is able to produce the output voltage which is lower or higher than the input voltage, which determines by the value of D. So you can vary the value of D from 0 to 1, and to be able for you to get the required output voltage. Okay, similar to the boost converter, we need to relate the inductor current and the output current. So because in the case of critical current, during the boundary between continuous and discontinuous, we need to consider the inductor output current, critical output current, the minimum output current. So we need to relate IL and I naught. Therefore, this will be useful by the auxiliary equations. V in, I in, whereby we assume that it's a lossless circuit. V in, I in equals to V out, I out, and therefore we have I naught equals to 1 minus D divided by D. I naught divided by I in equals to 1 minus D divided by D. So we're going to use this equation when we discuss on the boundary between continuous and discontinuous current operation. Alright, this is straightforward, don't worry. One more thing about the inductor current. The average of the inductor current is always IL max plus IL min divided by 2. That will give you the average between the two IL max, IL min here. That is the average current. Okay. Alright. So now, as I mentioned in the previous class, that we need to look at the boundary between continuous and discontinuous current operations in designing the converter, and also when in the perspective of a user, we need to understand, we need to determine the load current that we can apply to the converter so that it will still under continuous current operation. Okay, so the boundary between continuous and discontinuous current. So in this mode, we can see that the IL min, right? Can I go back to the waveform? So during the during the boundary, at the boundary, I cannot draw. I can draw this. It's so sorry. Okay, so consider that this is at the boundary. So IL min will be equals to 0. IL min will be equals to 0. This is the boundary. At the boundary, you can see that the IL touches the 0 levels and then it rises again. So this is a boundary between continuous and discontinuous current operation. Right. So therefore, we have this equation whereby ILB, the average current at the boundary, ILB, the capital I is denotes it is an average current. ILB equals to IL max divided by 2. And from equation 16, delta IL V in T on, or this equation, IL min is 0, IL max equals to V in T on. Right? So we can see that ILB equals to V in T on over TL, and also you use equation 20 and 18, 20 and 18 here. You can rearrange and then you can find out that the ILB, the average inductor current at the boundary, equals to TV0 1 minus D divided by 2L. Alright, now we're going to use this equation. At the boundary, at this supernode, at this node, if you look at the average current, not the instantaneous current, the average current, I in, again, we have IL equals to I in I plus IC plus I naught. But we know that the average IC, the average capacitor current, will always goes to 0. Why? If you come back to this capacitor current, the area of the negative area and positive area will be the same, right? Therefore, if you try to look at the average of the current of the IC, it is always 0. It's just like a sinusoidal signals. The positive and negative areas is the same, and if you look at find the average of that sinusoidal current, it becomes 0. So that happens also to the IC, the capacitor current. The area of the negative area here equals to the positive area, so if you take the average, it will be 0. Hence, therefore, you can find out that the average current equation, this is the average current equation, not instantaneous current equation, I in plus I naught equals to IL. So you use that equation, and this is the average, I naught equals to IL minus I in, since the average capacitor. Therefore, I naught critical equals to TV naught 1 minus D squared divided by 2L. Or for the user perspective, if you reorganize the equation, you can find that the L critical, the minimum size of L, equals to TV naught 1 minus D squared divided by 2I naught. Right? So this also need to be used to solve for these equations. So you have to replace equation number 19 in this equation for you to be able to relate and to get that equation critical. So if you are a user perspective, which means you buy the buck boost converter from the shop, from any shop, for example, you buy it, and that buck boost converter already has this L inductor size. So we, as a user, you understand that the minimum critical current can be determined by this equation. For that to be the boundary, at the boundary. And if you are a designer, you are given a specification from your customer, which the customer needs an output current of a certain output current. So you can find, you can build the critical, or you understand, you know that the minimum inductor size that you can use is determined by this equation. Okay, right. Now we look into the output ripple voltage. As we see, this is very much similar to the boost converter. If you look at the current equation, okay, come back to the the current equation. So during the turn on, when the switch is on, you can see that the output current, the capacitor current, equals to the negative of the output current, whereby we see that this is only a rectangular, right? And can we go back to the boost converter? So very much similar to this boost converter, whereby during the turn on, you can see that there is a rectangular area, okay, and determined by the dt will be the base, and the height will be the V0 over R, the current equation, which is V0 over R, and the base will be dt, which is the turn on time. So therefore, the output voltage ripple equation is similar to the boost converter, whereby delta V0 equals to dt V0 over RC. So that will be the last subtopics for the DCDC converter. So very similar. So we have D, the duty ratio, multiplied by the period T, multiplied by V0 divided by RC. Okay, so it's very straightforward, but again and again I would like you to fill in the gaps, between the lines here, so you can derive, so that you will you understand from one equation to another equation, the relationships, and how you get to the output, the final equation of this I naught critical, L critical, and also the delta V naught. Okay, so to test your understanding, let's look at the simulations. Okay, so you are given this the original circuits, original designs of the input voltage of 24 volt, and we have this the gating block of 1000 Hz. This is a switching frequency for the IGBT, and it is switched from 0 to 144 out of 360 degree. So you can work out what will be the duty ratio. So 0 to 144 is the pulse given to the IGBT. This IGBT. The size of inductor originally is a 2 millihenry, and we have the diode and the output capacitor initial design for the output capacitor is 4000 micro, and then the load is represented by 5 ohm. Okay, so I give you about 1 minute, okay, or 2 minutes. Can you calculate what is the duty ratio of this circuit? Okay, can I give you just a few minutes to determine what is the duty ratio of this circuit? Number 2 is what is the output voltage? Okay, given this component design, what is the output voltage? Number 3 is find the minimum current, I not critical, with L equals to 2 millihenry. So you need to determine the minimum critical current, so that we have a case of boundary condition. Number 4 is that find the value of L critical. We want to design the circuit such that the output current is 5 ampere. And finally, with L equals to 2 millihenry and the output current of 5 amp, so 5 amp, so I need to delete this first. Right? With L equals to 2 millihenry and I naught equals to 5 amp, find C such that V peak to peak is 2% of V out. So we need to determine what is the value of output voltage, and then the peak to peak voltage, the delta V naught, will be 2% of that V out. Okay, can you quickly do that? I just give you about yes, 5 minutes. So you need to use all the I naught critical, L critical current equations, the equations, and then you need to use the output voltage equations, and finally the delta V naught equations. Alright, or probably I can leave it to you to do it, since this is a face-to-face, a non-face-to-face blended learning class. By the way, again and again, I always emphasize on you to use the PC to assist you in understanding the circuits. So if you want to simulate the circuit, make sure that you follow this simulation control, whereby the time step should be very small, because your switching frequency is now 1000 Hertz. It's no longer 50 Hertz, but it's 1000 Hertz. So this will be the time step. And then of course, when you use a large capacitor, you need to understand that the circuit take a longer time to get into its steady state, right? Because you only analyze the circuit when it reaches the steady state. Therefore, your output voltage is stable. You get the inductor current is symmetrical. The output voltage is stable at the average value. Okay, so therefore, in this simulation, you can use 2 seconds, 2.2, and then print time 2.19, so that you can save the number of points. Remember, this is a demo version. You cannot save all data. You only allow 6,000 points, so you have to be clever in choosing when to start to record the number of points. So I advise you to use this simulation control for you to simulate and play around. This also can be used for your buck and also the boost converter circuit before. Right? Use this simulation control and to look into the output voltage. Okay. Alright, so try it, and this will be the answer to your exercise here. What is the duty ratio? You can quickly look into the angle from 0 to 144. That will give you the value of D equals to 0.4. With that 0.4 duty ratio, you can find what is the output voltage of the circuit, buck boost circuit. So it is 16 volt. So it's 24 to 16 volt. Now the converter work as a buck converter in the step down operation. find the minimum inductor current, find the minimum output current and not critical with L equals to millihenry. So the answer is 1.44 ampere. And the output critical, the lowest, the minimum output current is 1.44 ampere. And if you want to simulate that, of course you have to divide to get the R in the circuit. Therefore you can use a V out, R equals to V divided by I to get the value of R, and then you plug into the simulation circuit, and then you run, and then you can find current. Okay, can I do that? So now let's run it together first. This is an original circuit. So what is the duty ratio is 0.4. What is the output voltage is 16 volts. So can I simulate that and see, do we get that 16 volt at the output? Right, so V out, look at the IL to see whether it's in continuous or discontinuous operation, to confirm that it operates under continuous current mode. And this is my V out. Okay, look at that. We cannot put it together, sorry. I must remove the V out, leave that this is inductor current, and then get a separate scope for V out. Okay, so now we have the IL is continuous, V out. If I take the average of the V out, then you can see that the average of the output voltage is 15.97, or very much is 16 volt. Okay, so we have a correct answer there. Okay, right. Number 3, find minimum current, I not critical. So with L equals to 2 millihenry, the answer is I not critical is 1.44. So if you translate that with a 16 volt output voltage, that will give the value of R, the output current, output resistance of 11.11 ohm. So I want to change that to 11.11 ohm. With this circuit, I'm going to see the inductor current will fall to 0 and then rise again. And this is the boundary condition. So the inductor, the minimum current that allows for the circuit is 1.44 ampere, and that corresponds to 11.11 ohm. Want to run simulation again? Look at inductor current. Yes, if you look closely, the inductor current, it falls to 0 and then it rises again. And so this is the boundary between continuous and discontinuous. Hence, having said that, if I make it lower than that, the output current lower than that, such as the value of R is going to be increased, for example, to 15 ohm, I'm going to increase R, therefore the current will be reduced below than the 1.44 ampere. So let's see what happens to the circuit in that conditions. Run circuit, look at that, and now there is a intermittent. This is under the discontinuous inductor current operation, and therefore when we operate under this discontinuous current mode, if you look at the output current, you cannot apply that equation anymore. The output voltage equation, which is equals to V in multiplied by D divided by 1 minus D. It is always greater than the equations or the voltage found by that equation. V in multiplied by D divided by 1 minus D. So in all cases of a discontinuous current operation, even under buck converter, boost converter, or buck boost converter, when the current falls into the discontinuous current mode, we can see that I think I have demonstrated that the output voltage is always greater than the calculated value, which means the voltage under continuous current mode. So you have to take note of that. Alright, so this is a concern. So we know that the minimum size of the current that we can use with the L equals to 2 millihenry is 1.44, that is corresponding to 11.11 ohm, and re-simulate that. You can see that it is touched the 0 level here, and then it goes up again. Right, okay. Now let's do the find number 4, which is find the value of L critical. What is L critical here? With current, the output current is 5 amp, right? So what is the value of 5 amp? If you want to make the current, the output current is 5 amp, so it will be 16 divided by 5. That will give you the resistor of the value of resistor of 3.2 ohm. And so if you have a 3.2 ohm, that will give me the answer of the output current of 5 amps. And we want to find the inductor current, so the answer here is L equals to 0.576. I'm going to change that to 0.576, but make sure that you calculate that using the equation and get this answer, 0.576 millihenry. Let's simulate. Again, under this condition, we can see that the current falls to 0 and then rise again. Let's run the circuit. Yes, it's confirmed that the inductor current falls to 0 and then rise again. So this is of course at the boundary. And again, if you take the output average, it still gives me 16 volt, which is agrees to the equation that we used just now. Right. So number 5, with L equals to 2 millihenry, we change back to the original design specification, 2 millihenry, and I naught is 5 amp. Now we maintain the output current of 5 amp, 5 ampere. Find CH, we need to find what is the value of capacitor current, capacitor, such that the peak to peak is 2% of V out. So delta V naught is 2%. 2% of 16 volt. That will be 3.2, isn't it? Yeah, 3.2 volt. That will be 3.2 volt. So we have 16, so 0.02, 2%. No, it's a 0.32 volt. And we want to find that we're going to have the peak to peak of 0.32 volt, and I already have the answer. It is 6250 microfarad. Very large capacitor, 6250 microfarad. So I'm going to change that to 6250 microfarad. Okay, and run the circuit, and we're going to measure the maximum peak and the minimum peak of the output voltage. Run again. Okay, the inductor current is continuous, and this is the output voltage. If I take the average again, it gives me 16 volt. Now I'm going to determine the Vmax. Sorry. Okay, the maximum is 16.12. Can you take note of that? 6.12. Note that, 6.12. And then you have the minimum peak of 15.80. Do I get 0.32? Yes, it is 0.32 volt. So it's a precise, quite accurate if you use simulation, and therefore the simulation will help you to confirm your calculations. Yeah. So, but again and again, you need to simulate it correctly, properly, so that you get a correct waveform. When the waveform gets into a steady state, you can see that it is symmetrical. It is symmetrical, the inductor current is symmetrical, the output current is symmetrical. Let's say if you simulate it not long enough, for example 0.2, I'm going to reduce to 0.19 seconds. Let's simulate that and look at the waveform, whether it gets to steady state or not. Right? Look at that. If you look carefully, carefully, you can see that the inductor current here, this cycle is not the same as the next cycle here, the following cycle, isn't it? So therefore, and also if you refer to the voltage, the output voltage, it is not symmetrical. This is like the output voltage is still climbing. And look at that. This is the peak increase, it keep on increasing. So we have yet reached the steady state. So of course you need to increase the simulation time, increase the simulation time, make it longer, and then you can find it now you reach a steady state when you change that to 2.2, 2.49 second. Okay, I think that's it. Alright, so we have completed the DCDC converter circuit. Right, okay, make sure that you download all the final year exam questions, final semester, and try it out. I think most of the exams is quite similar, but you have to know all the equations here, and then try it, and good luck. Okay, Assalamualaikum warahmatullahi wabarakatuh, and thank you.